All right, so we've talked about MPI in the supercomputing workshop, in the session on Friday, and probably heard it mentioned elsewhere during the week. But, just to lay out the particulars, so MPI, that stands for the Message Passing Interface. It's an API that provides a framework for writing parallel programs following a multiple instruction, multiple data model. So by that we mean essentially multiple programs all working on different sets of data. So that could be copies of the same data, or it could be completely different data. But they are all working sort of independently with each other unless we get them to communicate somehow. And MPI is the de facto standard for distributed memory computing. And there are a couple open source implementations which you'll see just about everywhere, and they are OpenMPI and MPI-CH. The feature set between the two is pretty much identical unless you start to try using bleeding edge MPI features. But basically just use whatever is available or easiest to install on your own computer. And the basic idea of the MPI, sort of mentioned, is that you have these multiple processes, or basically copies of your program, and they work and run independently unless we ask them to communicate. And they do that by sending and receiving messages, which are basically just like packets of data. And this arrangement is why MPI is able to scale on supercomputers, right? Each node on a supercomputer has its own memory. And MPI basically is very comfortable in that framework. You can run MPI just on your own laptop, and you can get a speed up in that case. So in that instance, though, it's just important to remember that as the programs, from the program's perspective, each one of the processes is its own independent program, so the variables aren't shared. All right, so the MPI standard defines a C and Fortran interface for all of the MPI directives or methods or commands. However, you can use MPI from quite a few languages because people have written bindings to the C libraries. So bindings are sort of like, you could think of it as a wrapper written in one language that exposes the functionality of a library written in another language. And for Python, that package is MPI for Python. And it is a great package that pretty much gives us access to almost all of MPI's features. In particular, MPI for Python is designed to work very efficiently with NumPy arrays. And the reason for that is that NumPy arrays basically contain data that is that can be interpreted as a C data type. And well, because MPI is written in C, and also Python itself is written in C, and then NumPy makes use of these contiguous C arrays, it's very natural for MPI for Python to interact with NumPy arrays with very minimal overhead. So NumPy arrays are very efficient, and that's what we'll be focusing on in this workshop. So I guess on that, when I start talking about a NumPy array, who's familiar with that? Who here has worked with Python? worked with NumPy. And Jamie's used a bit in this time. If you want to lower your hand from earlier and raise your hand if you have, that'll give me a bit of a sense. And I guess for anyone who hasn't used NumPy before, NumPy is a very common Python library for performing mathematical computations. And the main sort of feature of it are its arrays, which like allow you to perform really, really fast, vector addition, matrix multiplication, sort of all of your sort of fundamental operations in linear algebra. And even if you're not, doing very mathematical computing, working with NumPy arrays where you can speed up your Python code. So I'm going to, we're going to move to our first MPI example here. And the website, ideally, you should be able to actually just click on the upper right of any of these code blocks and then copy and paste it into the text editor of your choice, even if that's in the terminal. One thing to watch out for is that MPI doesn't really work nicely in a Jupyter notebook. So if you're used to following along with Python workshops or writing a code in a Jupyter notebook, for this, fortunately, I have to ask you not to, and instead actually kind of, save your MPI code as its own .py file, and then run it from the command line. And to run or launch an MPI process, if you're on your own machine or you're like a Nimbus instance, the command you'll need is MPI execute or MPI run. It can change between Linux distributions, and pick a number of MPI processes that's greater than one. If you're on your own laptop, the most you'll probably be able to choose is 4, or basically however many physical CPU cores you have. So if you're not sure how many CPU cores you have on your laptop, start with 4 and see how you go. Now, if you're working in an interactive session on Sotonix, the equivalent command is srun, where importantly, note that the dash lowercase n defines your number of MPI processes. So I'd like everyone to try running this hello MPI example, and just raise your hand if it runs successfully for you, and leave a comment in the chat, or just speak to me if you run into an error. And then we can sort of start digging into what's going on in this code snippet. Good question, Lara. So it's okay to copy this code into a file that you created using that.
Hedrick,
What's up?
I've got it to run, but it seems to be a problem, I think, with the program script or whatever, because it's saying syntax error, invalid syntax, and I think it's pointing to where the problem might be. It's giving me the line. There's a little arrow under the, what's it called? Quotation after the full stop from size.
What version of Python are you running?
Is that F meant to be here? After the print, is the F meant to be before the colon, the comma, sorry, apostrophe?
Sorry.
See after the print bracket.
So the F. It's a thing called an F string in Python, which allows for a substitution of just variables into the string. So like in the curly sort of braces, you're able to put variables and they're substituted in. Now you need to be running, I think, Python 3.6 onwards for this to work, and most computers should have that. If Brittany, it seems like you might be running an earlier version of Python, which, well, it'd be good to move to a newer version. And we can chat about that later on. But for this workshop, I'm sorry about this. You'll
it says Python at 3.11, I think, in my that's too low.
Yeah, that's too early a version.
Okay. Yeah.
Sorry,
yeah.
I'll turn my mic off.
So what you can do is modify the print statement.
Okay.
Right. So, you could modify it to be something like,
would it be easy for me just to update Python, or is it a bit of a long process?
It might not be too difficult. You may be able to install a newer version of Python through brew.
Okay.
But it really does depend on your setup. You could, you can edit the print statement, right, to just get the same sort of information, though it won't be quite pretty, something like, you could do something like this. I'm just popping it in the comments.
Okay.
And you can, that's probably what I would do for now. And then
okay, so I just replace the F and all that in the brackets with that instead.
Yeah.
And then it should, okay.
Just
I'll do that.
kind of as you would sort of normally use the standard way you would use a print statement.
Yeah.
And in the intermission, we could look at upgrading Python.
Cool. Cheers.
No worries.
Edric. I have a small issue. When I ran the brew install commands, they installed into my local bin directory, whereas VS Code for me right now is in my Anaconda directory, and I've switched it out on the, I don't know if you use VS Code, but on the bottom right you can choose your interpreter, and I chose the path of where the brew stuff is. But my terminal is still stuck in the Anaconda. So if I go which Python, it shows me the path to the Anaconda version.
Do you have parentheses next to your cursor? Like, does it say like bracket base or bracket?
Yes. I guess it would.
So you'd need to exit out of the that Anaconda environment.
Could you remind me how to do that again? Source or conda or something?
Trying to recall. I don't actually use Anaconda itself. I think something like conda deactivate is the one.
Yes, that's right. Deactivate.
No worries.
Yeah, there we go. I think that should work. Yeah, thank you.
Great. Yeah, I don't use it, but I've messed around with it, so it just takes a second
Yeah.
to get the
Yeah, I was using it last year,
resolution.
and it's been a while since I touched it. So, yeah.
Yeah, some people really, yeah, it can really nice way to use
Mhm.
use Python.
All right, thanks.
Great. So get a show of hands to see who's managed to run the code snippet. Great.
Okay, now I'm getting an error saying there's no module named MPI for Pi, but it did install.
Mm-hmm.
I think that would be the same error I was getting, which is it's in the wrong path.
Oh, okay.
Yeah.
Sorry, where do I have
So-
to put it?
So a couple things you could do are try restarting your terminal, right? So just
Okay.
and then checking your Python version. That should be a newer version of Python. If everything's updated.
Okay, window. I put no, it's still 2.7.16.
Yeah. Okay, so the next thing the other thing we need to do is add your brew installed Python to your path. So basically where brew searches for Python. Does anyone here who uses brew? Could you tell me do you know where the brew installation sort of directory is? Can you recall? Yeah, I think that might be it, Akbar. So try running this command. Is it Carl and Brittany who are having an issue? So hopefully that'll list a directory and you see various Python versions, like the Python executables.
I'm still so I switched out of the Anaconda thing, but I'm assuming it's the same issue where I'm in my old Python version, not Python 3.1.3.11.
Yeah, and what system are you on?
I'm on a Mac.
And you're using Homebrew as well?
Yes.
Okay, so just in a fresh terminal, try running the command I just pasted. So what we're trying to do is just find where Python is installed.
Yeah. It's not running for me. No such file or directory. Yeah, same thing.
Yeah, I'm getting the same error.
Okay.
I think the command is slightly wrong.
It might be a little different. Either of you comfortable sharing your screen?
Yeah, I don't mind.
I can share as well.
Yeah, you'll have to stop sharing before I can.
Mm-hmm. So for everyone else, this is a good process to kind of take note of, because you can run into similar issues on any machine, so Linux or Windows. So we'd
If I
probably
go, if I go
Yeah.
which Python, it tells me this is the one, but in
yeah.
Yeah.
So could you try echoing through dash dash prefix? So that would be the path of the.
brew,
So with the dollar sign, sorry, as sort of included above. Yeah. Okay. And
I know
then,
the path because it's up here, in Python 3.11.
oh, well, that's what we're looking for. Cool.
Yeah.
So
How do I get that into my
what
path?
we can do is we can put that to the beginning, like, of your path, right? So where so that's Python 3.11. Try running the command Python 3.11. It's just a simpler fix. So Python 3.11 dash dash version. We'll see if it so be the Python
Python
3.11, like as you see it in
Oh, you said hyphen, sorry.
no worries.
Yeah.
Great. So try running please try running the example code, but with Python 3.11.
I'm not in the directory. Yeah, it looks like it's running.
I mean, it's taking its time.
I think my computer is just slow.
Even then.
Yeah.
Brittany, are you able to do something similar?
I've been following along.
Yeah.
It seems to be running as well now, but we'll see.
Yeah. So
does upgrading the version? Yep, it's done it. So it says hello from rank 0 of 1. Is that what it's meant to do? Okay,
exactly.
cool. Awesome.
So Carl, could you try just stopping that and then running it with the MPI execute, sort of -N2 command? There's actually launching it as an MPI process.
Oh, sorry. I think I have a firewall thing that popped up that in C. That's why it hasn't been.
That makes sense.
Um,
Kind of gives you.
So should I try the same thing? Just run it like the MPI execute, exactly the same way?
Yeah. So try running it with more than one process, and so take a look for that pop-up, and it kind of points to I think some of the inner workings of MPI. So what's going on, right? It's actually kind of starting up it's doing a bunch of network communication, essentially under the hood, to pass its messages, right? And that's how it's able to communicate over the interconnect of photonics.
Yep, so I just have to replace the Python with Python 3.11 in order for it to work properly.
Yeah.
Okay, cool.
I think that's the easiest solution for now. There are ways you can map it so that like your Python command is that by default, but we can chat about that the end of the workshop in the break if you're interested.
Yeah, mine's
that'd be great.
fine now. I think it was just the firewall stuff that I had.
Great. Cool. Well, we'll carry on. I hope this was instructive for some of the other folks here. So these are sort of path issues with Python executables. It's not just a Mac specific or Homebrew specific thing. I've run into it in my own projects, so it's good to be aware of those troubleshooting steps. So the sort of digging into this code snippet, what are we actually looking at? So when we launch, the Python interpreter using the MPI execute command, what we're doing is spinning up multiple copies of the Python interpreter. And through MPI, so MPI assigns each of these copies of our program a unique rank ID in a thing called an MPI communicator. So, the second line of the code snippet, com equals MPI com world. That's the default MPI communicator, and it basically contains all of the MPI processes. We're able to create other communicators, in particular we'd call these sub-communicators. And you can do all sorts of interesting things in creating these groups of MPI processes, but for the vast majority of cases, you don't really need to think about that. MPI com world is enough. And the MPI communicator, that's a collection of processes that communicate with each other by message passing. In this example, there's no communication, but we'll be getting to that shortly. And we've used two MPI methods, the get size and get rank. So the first one, that's giving us the number of processes in the communicator, and the second is giving us the unique rank ID. Now, who has, if you've tried running this program with a few times with more than one process, what have you observed? Does anyone like to chime in? Thanks, Daniel. Yes, that's right. So, yep, the order is different every time. So there's no synchronization occurring under the hood, and we can't rely on, a consistent order of execution because either these processes are truly occurring in parallel. Now, you can actually do a fair bit, to parallelize, embarrassingly parallel workflows, just using, just by launching multiple copies of the Python interpreter and just making use of the unique rank ID. But to get, more out of MPI for Pi, we need to start looking into some of the ways that it can communicate between processes. There's pretty significant array of different MPI methods that you have access to, but broadly they break down into a couple different categories. So they either implement something called a point-to-point communication. So that's where we have one MPI rank sending to another rank and the other receiving. So only two processes are involved. And we also have collective methods. With these methods, the entire MPI communicator is involved in that communication. And these two types of communication, so our point-to-point or collective, they can be either blocking or non-blocking. So a blocking communication will basically just pause those two MPI processes until the data transfer has completed. Non-blocking communication, in that case, the processes can proceed on to other program instructions without waiting for that communication to complete. So the latter kind of non-blocking case, that can be a useful way to speed up your program. However, they are sort of non-blocking communications are notoriously difficult to debug. So you have to be very kind of careful when you use them. So now we'll just be sticking with the blocking case. where, just really in practice, oftentimes the work you have to put into ensuring that your non-blocking communications execute in the right order, that often will just undo any kind of speed up. So yeah, blocking is fine for most cases. And we'll just be looking at methods today that send data between processes, but it's also good to be aware that there are these reduction methods which can perform simple mathematical or logical operations in parallel. Say if you have an array of the same length at each process, and you would like to see what the smallest element is at each position in that array, across all of the MPI processes, there's an MPI reduction method that you can use, but just want to kind of signpost that in case that's something you need, so you can go looking for it. We'll just be looking at the most common blocking point-to-point and collective MPI methods today. So this takes us to our second piece of MPI example code. And that is example of the send and receive methods. So this implements point-to-point communication. So where we're transferring between a sender and a receiver, and both of the processes will not receive until the data is transferred. Pitfall is that if we have a mistake in our logic, we can wind up in a deadlock where processes are waiting for a message that they'll never receive. And in that case, the program will hang. It won't return an error, but it'll also just never finish executing. So that's really actually the thing you need to watch out for the most when you're writing MPI code with these blocking methods. So I'm going to give everyone a moment just to copy this code across and run it on their machine. And feel free, if you get it up and running quickly, feel free to adjust some of the variables. So I'm just going to run it myself on Cytonics. With this portion of the workshop, I'm going to move across to sharing my terminal. I hope everyone has the website up on their machine, and if you lose track or are not clear about where we keep looking at, just please let me know.
Edric, I'm getting the same errors again, saying there's no module named numpy, et cetera, when I try and execute it using that Python 3.11.
So, okay. So you were able to use it previous, so were you able to run the hello world example
Yeah, I was.
Yeah. Okay. It may be the case that you don't have NumPy installed for
Okay.
this particular version. Now, a way to ensure that you're installing a package specifically for Python, say 3.11, is
Yeah.
to call the pip module through the interpreter. So I'm just popping that command into the chat. So that -m is basically saying I want you to use the pip module. So pip is a Python module.
Yep.
To install NumPy, and we're just ensuring that it's within Python 3.11.
Cool. I'll try running it again.
So here's the bit of example code. Couple questions. What will happen if I run this with more than 2 MPI processes?
Is every processor but the 0th one going to try and receive data? Is that what's happening here?
Good suggestion. Not quite, though, because in the receive command here, with the send command here, we've specified a specific destination. So that's the rank with, that's rank 1, right? So that bug says that the other processes will receive nothing. Yeah, and that's correct. They're not really doing any work. I don't think the program will hang. So let's see. If I run it with, say, 4. Yes, run, not the sun. It's a very intense command. I just correct. I'll expand my allocation. So I suspect that if I run this with 4, we'll find that we see the same behavior, but the other processes, they'll just basically run right through to the end and just wait for the rest of the program to execute, having done no work. That's not really an issue in terms of the program logic, but it's something to be wary of if you're running a long MPI script on a supercomputer, right, where you're getting billed against your allocation. It's even worse than that. So you might have actually tested it out, Akbar. So it's correct, it just hangs. So we've finished the rest of the work, but our program is just it's just hanging there. No work is being done. So it'll just keep on running, right, until it uses up my entire interactive session. Another question. If I change, if we were to change the last if statement, like so, what sort of behavior would we expect? Yep, right. So that would also be a deadlock. So just to illustrate, so I'm going to run it on 2 processes this time. And you'll see, right, I'm not getting an error, like nothing is occurring because the program hasn't actually hit like a fault, a detectable fault in the sort of process logic. Right, you know, like you can kind of see, right, that from like rank 0's perspective, you know, we're creating this array, and then we're setting up a send to rank 1. Rank 1's perspective, okay, we're creating an array to receive from rank 0. And then, oh, we're to receive, and then we're waiting for a receive operation from rank 1. And you might think that that would return an error because, you know, it's rank 1 expecting a receive operation from itself. But we're not so lucky. That passes perfectly fine, the interpreter, and our program just hangs forever. So I guess beware.
Sorry, Edric, to sound stupid, but
No stupid questions.
what's the output meant to look like? Because I got 2 zeros in brackets and it's just stopped after running that. Is that what's meant to happen?
Exactly. Yeah.
Okay, awesome.
Yeah, no, great question. Should have, you know, ran the program, right? Without errors before going into how it doesn't work. Yeah, so just, you know, this is what I expect everyone to see.
Oh, awesome, cool.
An array with 2 zeros.
So does that mean the data's transferred?
Exactly.
Is that what we're doing? Okay, cool.
Yeah. So what we've done is we've created at rank 0, we've created an array, which it just contains 2 zeros, right? So rank 0, we just created a Python list with 2 zeros, converted that to a NumPy array.
Yep.
And then we've created another array at rank 1. Importantly, though, like, you know, everyone should note that this is an empty array, so it contains no data. So if we try to print it, probably just be a garbled mess. And we're sending our send array to rank 0, and it's receiving that data into the receive array. So it's not like we're sending the receive array object, where I'm sending the data that's contained within that object, so a copy of the data.
Yeah, cool.
Also, moving back over to the site, we need to just, you know, take a moment to, I think, talk about data buffers and data types. So, you know, it's just, you know, saying then that when we send information, it's not like we're sending the variable, right, and its associated data. We really are actually just transferring data that is contained within that object. So we're creating a copy of that at another MPI process. And we have to do that because each MPI process, I said earlier, has its own memory space, so its own namespace, its own set of variables. So none of that is shared, right? So we have to produce an actual copy of that data. Taking a closer look at the receive method, you'll note this, you know, pair in the square brackets, the receive array, and then this MPI int. This specifies an MPI buffer, so that a buffer just refers to some data structure, basically an array, that can contain the, information to either send or receive. And the MPI int, that refers to the data type of that buffer. So we're saying that receive array contains integers. The data type really matters in MPI. If we pick the wrong data type, it'll basically try to interpret the bits contained within that buffer as that data type, and it'll either return an error because it will see an unexpected amount of memory, or even worse, the program will execute successfully, but your data will be completely scrambled. I'd also like to point out that for all of the MPI methods that are designed to work with NumPy arrays, they all start with a capital letter. So you will also see com receive with a lowercase r. They're for something a little different that we'll touch on in a few examples. And yeah, just so here's a list of some of the MPI data types and their corresponding NumPy data types. So we've got, real, double, integer, complex, double complex, and they basically correspond to our single precision or double precision floating point types or single precision integer types. If you've not encountered the idea of a floating point number, I'd just say that, on a computer, right, we can't represent certain fractions to absolute accuracy. Like we have to approximate it at some point because we only have so many bits of information per number. So when I say a single precision or double precision floating point, I'm basically talking about the precision that we're able to sort of achieve using that particular type of representation in memory. Say for a single precision floating point number, we'd usually be able to represent numbers up to the 10 to the sort of -8th-ish position in the decimal number. And double precision, it's around the 10 to the -12-ish place for a decimal number. If you're doing machine learning, you're probably working with single precision numbers. If you're doing simulations in physics or mathematics, the standard is to use double precision. It's just really a matter of how much you care about speed versus the accuracy. So if we're looking back at our send and receive example, see that I've actually created a very specifically, I've created a NumPy array that contains integers. And then when we carried out the send operation, specified that it's actually the integer data type. So it's important that these the two attributes, it's important that they match. So that was, point-to-point communication. And in theory, you could carry out pretty much every MPI sort of blocking communication using only point-to-point communication. However, your code would get fairly tangled, and there are other methods which are more optimized under the hood. And in particular, right, these are useful if we want to carry out like a collective communication. The first of these we'll look at is bcast, or broadcast. And what this does is it sends data from a root process, so one of the ranks, to all other processes in the MPI communicator. So I'll just give everyone a second to run this code. And, maybe before you've even run it, what sort of output do you expect to see? Can anyone take a guess? I'll switch over to my terminal. All right, so back over here at Tonics. a little error in my copy and pasting. Oh yeah, semicolon. Cool. So we've got all of these received 1, 2 at rank 0. What's going on? In this code snippet, we're creating an array of length 2. Then at rank 0, I'm filling this with some data. So creating a new array, which contains the values 1 and 2. In this case, they are double precision numbers, so float NP float 64. Then I'm carrying out this at every single process, carrying out this broadcast operation, which is then sending the data that's contained within array to every other rank that is not equal to 0. So 0 is sending its values to all of the other MPI ranks or processes. There are a couple little things to watch out for here as well. For instance, you might be tempted to carry out the following. So at rank 0, I'm going to create my array, and then I'm going to broadcast it to all of the other MPI processes. But if I run this, I run into this name error. So name error, name array is not defined. Now, this error, we can see it's been triggered a few times, right? 1, 2, 3. So it's triggered up 3 out of the 4 MPI processes. What's going on? Well, taking another look at our code, we think about the flow program for one of the processes that isn't rank 0. Great, get up and running. I know what my rank ID is. I skip over this entire block because I'm not rank 0. And then now I have this broadcast operation where I'm using this buffer array that hasn't actually been defined. So it's an undefined variable at that process. So for the broadcast operation, it's important that we actually have array defined. Another small pitfall that I've fallen into here actually is, I've created it at all of my MPI ranks, but then when I go to operate in a rank 0, I'm creating a new array, but just with the same label. In terms of our program logic, that's fine. But if I'm, creating a lot of very large arrays, that's sort of memory inefficient. So really, it should just be assigning values to the array that's already been created. So that's more optimal. There we go, everyone's happy. Cool, any questions about broadcast? This section's a little on the dry side, but what we're moving to is a set of case studies where we'll be thinking about how we can apply these operations to actually parallelize some non-parallel Python code. So I'm hoping there we can have a bit more of a discussion. Cool, I assume everybody is on board then. Cool. So moving on to scatter, this is another example of collective communication. I'm going to just bring that example across to a session in Cytonics. So scatter, what this does is it takes an array and it distributes it equally over all of the other processes in that MPI communicator. For it to work optimally, it requires that the number of MPI processes, so the size of our communicator, requires that is a divisor of our array length. Otherwise, one of the arrays will receive no elements. There are scatter methods which allow for the sending of unique sort of length arrays to each process, but we won't be looking into it here. And in most cases, it's possible to write your code around this restraint while just benefiting from a shorter development time and easier debugging. So looking at this example here, at every rank, we're creating a receive array. So this array is empty and it's going to receive the data that's being scattered. And then again, at rank 0, populating this with some data. This could be, maybe from data that's loaded from disk or from some other calculation. In this case, I'm just creating an array going from 0 to 2 times the size of the array. So that should be enough to send 2 elements per rank. And because of that little pitfall we highlighted with broadcast, I need to make sure that send array is defined at the other processes, even if it's not being used. Now, the standard way to carry that out is just to set it to be none. So rank 0, it contains data. Everywhere else, send array is just none. And that means that when it appears in this scatter operation, which has to be called by every member of the communicator, we don't run into an undefined error. Now, the syntax of scatter contains 2 buffer pairs. First of those is our send array, so the data that we're sending and the data type. And the second is the receive array, so where we're going to receive that data, and again its type, and the route, so where we are sending, where we're scattering from. So let's take a look. Oh, you can see I've taken my array and I've scattered that to all of the other processes. We really wanted to convince ourselves that it's worked. Let's print the send array. And I'm actually going to pass print this keyword argument flush. So what that actually does is it prevents Python from buffering the print statement. So typically what Python will do is it will take a few print commands, sort of queue them up, and then at some point it will flush them to standard out. And that's just a way of preventing your code from being slowed down a huge amount by these repeatedly having to print a screen. When you're running an MPI program, though, it can be useful to override that, because it can be nice to see things printed when that line of code is actually executed, right? So here we're going to hopefully we'll get the send array printed before the receive array is printed. Cool, and there we go. So I can see, right, rank 3, our highest rank, has received the last 2 values. Rank 0 has received the first 2. And that's MPI scatter. A natural question is, what if I want to collect elements? Can MPI do that? Yes. So we have this MPI method called gather. And it really can be thought of as the sort of like the inverse of our scatter operation. So it looks fairly similar to our scatter example, but the logic's sort of operating in reverse. So here we're creating a send array, and it just contains, two lots of the rank ID, each MPI process. And then at rank 0, we're creating an array to receive all of these values. Everywhere else, we're setting it to none to prevent that undefined error. And then we're recalling gather, and it has the same general pattern as scatter. So we've got our send buffer and its type, the receive buffer and its type, and a root process. If I run that, right? So you can see that we have 0, 0, rank 0, 1, 1 at rank 1, 3, 3, rank 3, 2, 2, rank 2. And we've received all of those values at rank 0. And, I think it's quite handy to have these operations, and that they, take care out of the ordering of our data for us. That it's just placed into the array in the order of the rank IDs. It's quite nice, right? You don't have to sort that all out yourself. Any questions about scatter and gather? Okay, well, this brings us to the last of our code snippets, where we've been building up the atomic operations that we need to parallelize some of the examples we're going to look at in the next half of the workshop. So I'm going to take a bit of a detour from working with NumPy arrays, and instead we're going to look at how we can send and receive Python objects. So there are specific methods for sending and receiving Python objects. So this is basically just anything that isn't a NumPy array. But these commands are really useful because they're super flexible. However, they are much slower than working with NumPy arrays. So I would resist the temptation to continue to work with like NumPy lists if you're doing something numerical. And then just sending and receiving those lists, if those lists are large or if you're sending and receiving frequently. The reason for that is that to send a Python object, MPI for Pi first converts that Python object into binary. Basically, pickles the Python object, if anyone's familiar with the Python pickle module. So the thing that allows you to save Python objects as binary data. And that introduces quite a bit of overhead, right? So every send and receive, you have to perform that encoding step, that pickling step. But they're often very useful, especially in the final or initial stages of your program. And where you will use them, and where I do use them, is to send and receive scalar values. So in this example, we're using MPI broadcast to send a truncated value of pi from 0 to all of the other MPI processes. Now in practice, right, this like X would maybe be an average value or something else where we care about, our data set. And the logic is similar to the earlier broadcast example. So, X has to be defined at all of the MPI processes. But the syntax of our broadcast method, it looks a fair bit different. Firstly, we see that B is a lowercase, not an uppercase. So in MPI for Python, all of the commands or methods that are in lowercase, they can work with Python objects, so lists or individual numbers, or even a Python dictionary. And then all of the commands for NumPy arrays, which are the super fast, efficient commands, they start with the a capital letter. Also, for these lowercase commands, we see that the received value, it's not going into a buffer, but it's actually being returned as as you would see for any other Python function. So they kind of behave much more like a standard Python functional method. And if I run this, I should see that 3.14 has been sent to all of the other processes in my communicator. Good Lord. Examples. Though there's a small typo in that example. My apologies. I'm missing the F. So that's the thing that tells Python that I'm using an F string. There we go. Right, we've broadcast our Python object across the communicator. So this takes us to the end of this section. So we've seen some of the basic building blocks of MPI communication. And with this, you can really go off and actually start to write parallel programs. But to aid with that, we'll be moving on to a few case studies where we'll be seeing how we can apply these communication directives or methods to parallelize pre-existing ordinary Python code. Before we break, it'll be a good time to hear any questions anyone may have. What do you think about the complexity of MPI so far? How does it seem to you?
I have a question about MPI and its uses.
Yeah.
Is it only used for like mathematical analysis and physics, or are there other domains that people can use MPI for?
So it's most common, I'd say, like in numerical, like computing, physics, mathematics. But you can use it far more broadly. So one of the examples we'll be looking at is sort of an image processing example. So yeah, it's not constrained just to numerical computing. Like when we're looking at something like the gather example. So here, right, I'm just filling up the receive array with But I'm here filling up the send array with just the rank, right? But this could be the output of any process. So we could have, a whole bunch of, like other stuff happening here. Like maybe a program that's working on different subsets of a large database, all in parallel. And then this gather step is just being used to kind of like collect together your final results, for example.
Oh, okay, yeah.
So like everything else you can do with a Python program, right, is still on the table. We're just now able to introduce control logic that takes into account the MPI communicator. Good question.
Cool, thank you.
Yeah, and that's I think a common reaction chain. Like, yeah, it seems pretty straightforward, but yeah, not entirely obvious how it can be used yet. And yeah, I think the best way to kind of get a sense for that is to try applying it, right, to a few examples. I found that when I was sort of learning it, the moment I needed to do something in parallel and sort of looking for that kind of speed up, things began to kind of just fall into place. So it's sort of a different way of thinking about programming and writing code. Tina, so Tina's asking, what's the difference between MPI and the built-in multiprocessing module? So the multiprocessing module in Python, that is, firstly, it's designed for a shared memory context. So you have a single instance of the Python interpreter, and all of the processes are operating on the same like physical computer. They have the same memory and the same set of variables. So it isn't able to scale across a distributed system like Photonics, Topaz, or another supercomputer. Also, in general, the sort of Python multiprocessing is more of an example of concurrency as opposed to parallelism. So it'll be a switching between these different tasks, more than likely, like one after the other, but they won't necessarily be executing in true parallel. And that's because Python has some sort of protective mechanisms built in to it that kind of control how many independent processes can have running at any one time. But I think that's changing a little in the newer Python standards, but as just a very broad summary, multiprocessing, it's more a case of concurrency. It's very useful, but it's not necessarily true parallelism. And then it addresses a shared memory context where you're working just on a local machine and everything has access to the same. No worries. Great, so let's break for let's take a longish break. The next, let's meet back here at 11:20. How's that for everyone? Enough time to take a stretch and yeah, hopefully answer an urgent email outside at the very least. Cool. Great. So I'll see everyone back here then. Do we have any other questions come to mind during the break? Cool. Okay. Well, let's move on to our case studies. And what we're going to do is look at some Python code, and together we can kind of think about how we could go about parallelizing these processes, looking at some practical examples. Now, for our first example, we're going to look at an example of a Monte Carlo integration. The specifics, sort of the mathematical justification, I suppose, of it is, not essential to go into here, but the basic idea of what this program is doing. I'm trying to draw on the screen. Let's see how I go. Okay. Basic thing it's trying to do is estimate the area of a circle. And in Monte Carlo sort of integration, what we do is we kind of consider the area of our function. So here's my best attempt at drawing a circle. And we, so we have our function, we put some kind of box around it. And then we kind of make the observation that if we pick random points, you can always think of it as like throwing darts at the board with a blindfold on. The number of points that fall within our circle or our function will have some correspondence to its area, right? So, if I just start picking these random points and checking to see whether or not they're inside the circle. So I have a total of, so a total of n points, or n random points. Over time, I'll arrive at this ratio, so like n. So our number of hits, so points inside, divided by n, is going to be proportional to the area. And to retrieve the area from that ratio, we simply multiply it by the area of our bounding box. So this is length 2. Our area would be 4. So 4 times the number of hits divided by our total number of random points will tend towards the area of our circle, which this example will tend towards pi. So we can see this process in the Python code. To find this function, mcpi, start off with, we pick a certain number of hits, so that's n. Starting at hit 0, we loop through and generate a random point within our box, right? Length 2, so it's going from -1 to 1. And we're checking to see if that point lies within the circle, right? So the line of that circle, that's a constant radius of 1. So we're checking to see if that point is within that radius. If so, we add it to the hits, and then finally we return our area, our estimate for the area of our circle, estimate for pi. And yeah, the more samples we take, the more accurate it is. See here, it takes quite a few samples to arrive at an accurate result. So let's just try copying this across to our own machines and run it. And yeah, I'd like to hear what value you get. How close to pi is it? Great. Yeah, so we're all getting some sort of something close to 3.14 with variation in the last, or variation in the third decimal point. So it's not the most accurate. We want to get a more accurate estimation, we're going to have to up the points. But you probably noticed that it already took a little bit for it to execute in your machine. It's a acceptable amount of runtime. So this sort of program is a really great candidate for parallelization with MPI. I'm just going to switch across, log into Cytonics. Okay, so think about the structure of our code. We can sort of figure out how we could go about turning this function to, making this function parallel. And with MPI, it's often really nice to actually start off just with pen and paper, kind of drawing a diagram that sort of outlines the communication that's going on. So we've got, what sort of processes do we have here? So we've got our function, and what it's doing is it's like generating a random point and then it's checking for a hit. And then it's summing. To the hits conditionally. Now, any suggestions? How could we start to approach this problem in a parallel way? How can we get some sort of a speed up? We have to pick some portion of the code, right? That we're going to run duplicates of across our MPI processes. Great. Yeah, Ethan, that's it. Spot on. So like generating the points and checking to see if they're a hit, that's all independent. So they can be done on multiple processes simultaneously. So we only need to communicate the end to sum all of the points. So all of this, right, that can be done in parallel. And we can also have, our own. Yeah, and it's great, Jamie. So we can have each process can sum and then average out the sums at the end. Yeah. So this step, that can occur locally as well. So we'll have a local value of n. That's what you meant as well, Ethan. It's great. So we're all coming to the same point. All right. So which of the MPI commands do you think could be useful here? Don't worry about specifying like the exact syntax. Once we've just identified, what they are, we'll step through working it out in practice. So scatter. Okay, so what are we doing with scatter? How does it fit into the pipeline? So we'd use scatter to send data to all of the arrays. Is there a step in this process where we would need to perform that operation? Feels like, sort of along those lines, right? We need to get our final value. Okay, broadcast used first, send data to all of the processes. Yeah, we could use that. What data would we be broadcasting to all of the processes? What information do we need to broadcast? Okay, so like broadcasting an array of hits. Well, I see where you're coming from, but we can actually avoid needing to broadcast because we can just create, we can create our hits array, our final hits array. And that can just be created at each process. Or, if it's not needed, if we have an array, or just storing a single value and then an array for storing all of the values, it can either be created or set to none. So we don't actually need to communicate that. Exactly, Brittany. Yep. That is, I think that's how I would go about it. So we can, the final step, right, to get our global value of n, would perform a gather. So yeah, we'll gather all of the local n's, and then we can do the sum and the or the averaging at one of the root processes. So that's just, we'd normally do that at rank 0. And what I like about this, so once we've kind of got our process here, it's nice to draw almost a graph representation of this. So we're going to have multiple MPI processes, all getting a local value of n. Then we'll pick a single root process. Let's pick rank 0. And then we'll be gathering to rank 0. And that's where we can get our final value for n. Okay, now for some coding. Okay, so let's implement this plan. The first thing we'll need to do is import our MPI module. Without that, our code won't know that it can run an MPI parallel, and there'll be nothing to kind of spin up those processes, create a communicator, assign a rank, and all of the other work that MPI for Pi will do for us in the background. So I'm going to add that import statement from MPI for Pi, import MPI. Next, we'll give this another argument, com. So that can be our MPI communicator. And I'll just add this like that below. So com MPI com world. Modify our call. Now, let's just treat, so we have a value of n, and we want to divide that up between all of the processes. So our n local value, we can just set that as divide that by the size of our communicator. And And so we've got a hits. We let each rank use that. Just adjust the range now so it occurs over that smaller set. And we can carry out our MPI. Gather step. So if the rank is equal to 0, let's create our we'll create an array. And integers, else it's just going to be none. And because we're working with a NumPy array here, as a small quirk, we need to have our hits inside an array, even though it's just an array of length 1. So all of the processes will just redefine hits as a NumPy array, length 1. And now we can write out our gather operation. So we're going to send hits. And receive it at ends array with the root process being 0. And then if, so I could just define a rank variable, but we'll just get the rank. If that's equal to 0, we'll get a final value for n. It's the average. And final value for our area. Sorry, final value for hits. I'll just call that hits global. And sum up hits global, and we'll compute our area as 4 times hits global divided by n. Otherwise, just assume that we only need this value at rank 0.
You'll have to divide by n local, won't you? Because you averaged rather than summing the individual totals.
That is correct. That's why I just changed it to a sum instead of a
Yeah.
instead of the average
Yeah.
to keep the structure the same. But yeah, well spotted. Yeah. So otherwise, we'll just set area to been done. Just assume that we only need this at the root process, and yeah, and we return our error. So what I'd like everyone to do is, hopefully from following along, I'd like you to modify your version of MCPI accordingly, and then try running it on your machine with one, then two MPI processes. And yeah, let me know your result. Or if you run into any errors. But that's correct. Yeah, you get a depreciation warning if you use NumPy int, MP int instead of int. And that's just because even previously NP int is just an alias to Python, the Python integer. And they're removing that from the package eventually. I have the np.int ingrained in my muscle memory, so I'm having trouble breaking out of the habit of defining my NumPy types that way. So yeah, just for everyone else, you'll run into a depreciation warning, not an error, but depreciation warning if it's np.int, and that'll be fixed if you just declare it as a like a Python integer type. Great. Yeah, so are we seeing 3.14s? Just raise your hand if you, no worries, Jamie. Raise your hand if you manage to get things up and running. And we'll just, yeah, hang at this point until everyone's had a good chance to see this on their machine. In the meantime, so I'll talk about a couple of the some finer points of this process. So when you're performing something like Monte Carlo integration, or any process, right, that has this pseudo random number generation like element to its execution, if we want reproducibility, it's pretty common to set the seed of your random number generation at the start of your program. So a simple way of doing that in Python, rich random number generation is np random seed, and then you just pass it some integer. say 0. Now, if I do that here in my parallel code, I'm introducing a subtle but pretty significant bug. And it's related to my reliance on random numbers in the integration part of my code. Is anyone able to spot my mistake? I'd like to take a stab at it. So, when I set the random seed, like the idea is that I will get the same sequence of random numbers every time. If I set the same seed at all of my MPI processes, I'm no longer performing n, differently generated, right, random points. I'm no longer integrating over n random points. I'm actually integrating over, n divided by the size of my communicator random points that are each being repeated size times. So I'm, because setting the same seed and it's just going to have the same sequence of random numbers. And again, that's something that's very hard to spot because it doesn't return an error. But I've added a correlation to my system that's, not there by design. So a way to work around that is just to simply use the rank as the of your MPI process as your seed, or at least use it as the basis for seed generation or for your random seed. So get rank, just pass that rank as my random seed. Now I'm benefiting from reproducibility on my target system. And I'm ensuring, right, that I have a unique sequence of random numbers at each process. So for those who have executed your code correctly, I think it'd be great to see if you actually do get a speed up on your laptop. So there's this function time. I can't recall if it was introduced in the introductory workshop or if you saw it in the supercomputing training. Great. So Ethan, you saw a noticeable speed up. Fantastic. So one way you can get a number for that is to run it using time. So if I was going to just run this with just a single thread without the MPI launcher, like time, Python. And what that'll do is it'll give me a value for system time, CPU time. Well. Okay. The important thing though is we have this value real. So that's the wall clock time. So the actual program runtime is read from the clock on the wall. So what would be interesting, I think, is to run your code with one MPI process, timing it, and then 2, and then 4, or ever many cores you have access to in your machine. And I'd be curious to see how much of a speed up you get as compared to the single-threaded, non-parallel case. Anyway, thanks, Jane. if you're encountering the depreciation warning, we just need to replace np_int with just int in the line of code that I've got highlighted. Now, I'll unhighlight because you can't read a thing. I took that. There we go. Yeah. So it's just int on this line.
It's actually in another line as well, a few lines below that.
Ah, thank you. Thank you, Ethan. Yep, so pretty much everywhere you see it, just replace that. There we go. That should remove the depreciation warning. What text editor are you using? Nano. Let's see. So that's errors coming across because Python indentation is important in Python, but it can only be either tabs or spaces because those two characters are actually two different characters from the terminal's perspective. So if Python
So if I'm
encounters
using
the two,
tabs and spaces, then that's why I've screwed up.
yeah, exactly.
Okay. Okay.
Now most other editors, right, they'll be set to convert spaces to tabs or tabs to spaces somewhere in the menu, but because Nano, right, it's just very direct, straightforward, simple editor, it doesn't perform that conversion. Now,
Okay.
there's probably a way in Nano to convert all of your tabs to spaces.
Yeah.
But I'm not actually sure of that off the top of my head.
So I'll just rewrite it all with just spaces.
You may be able to run this command on your file. Now, let's see. Try giving that a shot on the command line. I haven't used that before. That might just perform the conversion for you.
It's telling me it's an invalid option, and then it's given me a whole bunch of things I can do.
Well, yeah, we may need to just leave that for now.
Yeah.
But future reference, yeah, stick to using tabs for the workshop is what I find easiest. So anyone else, sort of watch out for that. It's a pretty easy thing to run into with Python. Okay, we're just moving on from this in a moment. I'm just going to switch to the system that I'm using. Satonic seems to be pretty busy at the moment, so the having trouble getting an interactive session. Okay, so how are we all getting on? Is anyone encountering an error that they would like to share with the error message they'd like to share with the group?
I just want to double check that I'm getting the right output. So all I did was I just pasted it into Word and removed formatting, and it worked. I just got the 3.14 number at the end. Is that all I'm meant to be getting?
That's exactly it.
Okay, awesome.
Yeah.
And I did get that
That's-
warning as well.
You did get it?
Yeah.
Yeah. So that would be again just changing the NP ints to just ints.
Okay, cool.
Sorry about getting the. Can you all hear the computer giving me a thing super loud, or is that just through my headphones? You can't hear? If so, that's very nice. Fantastic. Okay, good. I can bear it. That's good to know. I'm not blasting you all with the sound. Okay, let's move on to the next case study, and I'm happy to loop back around to this one later on in the workshop, or towards the end, or in the week if you'd like to move through it. And consider like a different use case, one that goes outside of numerical computation. So for this example, we're going to be looking at a very simple image processing pipeline. And I'm going to share in the chat a link to a zip file of images that we can use for this exercise. Because unfortunately, I've noticed that the link in the website is broken. So please download the images from the link in the chat. Apologies. You may have some issues with that. The one below it should do it. A link, it's like a link to the file on the GitHub versus a link to the actual contents of the file. So on my system where I'm working remotely, I was able to download it using wget. You can also just press download. It depends whether or not you're working locally on your own machine or you're working remotely, in which case you'd need to download it using a link in the command. Great. Let's take a look at the code. So where in this script is set paste. In this script, we're working on a directory called images, contains a bunch of JPEG files. And it's a collection of dogs and cats taken from this Oxford pet data set. And we want to resize the images and then output them to another directory. To do that, the script's using glob to get all of the JPEG files in the images directory. We're defining our output path, resize images. We're using the OS method make directory to create our resized image directory if it doesn't exist. And then we're looping through all of our images. And all we're doing, you could be doing some other operation, but in this instance, all we're doing is resizing the images to 64 by 64, and then we're saving that image. Now, we've got a fairly small data set, this example, so we could all download it quickly, but I'm sure you could appreciate if it was a much larger set, the sort of thing that you might be using for a machine learning project. This could be a relatively time-consuming step. Now, well, I happen to have an idea of how I would go about addressing this with MPI. but just like before, we need to just identify what is the time-consuming step that can be performed independently in parallel. Who would like to make a suggestion? Yeah, that's a great suggestion, Akbar. So we could get all of our output paths and we could scatter them. So in that case, and that would do two things for us, right? So we'd be getting all of our paths, assuming that it's that, divisor, and, by doing this scatter, it's automatically breaking it down into an equal workload per process. So it's kind of sorts what could be a bunch of bookkeeping for us down our end if we were to try and divvy it up some other way. So the way I would approach that is I would first, get my import MPI for pi. Just define a shorter variable for my communicator. And then, unlike the other example, I will actually define a rank variable. Save some characters. And so rank 0 can be responsible for getting all of the file sizes, sorry, all of the file paths. And then we can perform a scatter. So here you can see that I'm using the Python object version of the scatter operation because my list of image paths, right, that's a list of strings of variable length. And I could send that as a NumPy array of data. That would be fairly involved figuring out how I'm going to format it. And because the sort of memory intensive part of this process is the image processing portion, we can afford to perform this initial single scatter operation at the start of our script. And in doing so, I've just ensured that image paths, right, I've redefined it at rank 0 as well. So it's just the same at all of the other processes. So we can just alter our code minimally. Yes. Okay, great. I'm glad you've gotten to that point, Brittany. So we're seeing an error. File exists error. Resized images. Now that's because there is a bug in this code. There's something else we'll need to address for it to work correctly in parallel. Like to hear from someone if they can they want to hazard a guess as to why we're running into this error. That's correct, Akbar. So each process is trying to make the directory resized images. And someone else like to suggest a solution to this error? Or are we just destined to forever be stuck, crashing, as all of our processes try to recreate resized images? Thanks, Ethan. Yeah, so we'll just encapsulate our make directory command in a if rank is equal to 0 state. And there we go. Let's think about how it'll work the rest of the program, right? So now, when we go to path, image paths is going to be a list of paths. There's a sub list of paths at that particular rank. It's now going to go through each of those images, performing the resize, and then it's going to just create and save that file to our resized directory. So we don't actually need to change very much of our pipeline because it's an embarrassingly parallel task. Brittany, so you ask, good question. So does only the root have access to this directory? Actually, all of our MPI processes can see that directory, and that's because they all have access to the same file system. So while they don't share the same memory, so when we say memory, we're really talking about RAM. So while they're running, they don't share the same variables, but they can all load data out of the hard drive or out of the storage. So in that case, it's not like they're all performing the one read operation that gives them access to the data. Think of it more so as like each MPI process can do its own unique read or write operation. So as long as we create our directory before the other processes start to write into it, everything's happy because they'll look in the directory, see resized images, and be able to perform that save. Okay, so you've run into an error. So expecting 4 items, got 58. On what line of your script is that occurring? Okay, let's check my coding there.
You just introduced another error with that copy paste you did because you didn't take the output path variable with you.
Yes, thank you. So just to back up there, just moved the creation of the output path to be before our scatter operation. So we can always be confident that the file, like the directory, is created before any of the processes try to save to it. Wouldn't have happened before because we're performing this collective scatter operation. But if we introduce other MPI logic further down the line, it's sort of, we're getting ahead of any potential issues there. So that's just a separate thing to the scatter. So let's take a look at the scatter operation, what's going on there. Okay, so we've encountered, we noted earlier that it tries to divide all of the elements evenly across the communicator. So the thing we should ask is it able to do that, right? Are a number of MPI processes, is that in the divisor of our list of image paths? Now, a way we can just check that is when we perform this glob operation at rank 0. Let's just print out the length of that list. And because we know it's going to run into an error, we're just debugging. You can always put in an exit here, so it's called by all of the MPI processes. So what do you find the yeah? So let me know if that could be the issue. So do we have an issue where we're not able to divide our images up evenly with 4 processes, say 2 processes? Great. So what is the length, and how many processes are you running your code with? Yeah, so 58, not divisible by 4. So that's it. We can't use scatter. Or maybe there's a solution. Yeah, what if we have a prime number of images? It's a good question. So there's a few different ways we could approach this. One means of mitigating this would be to basically figure out the nearest divisor of our the nearest list length that would be a a multiple of our communicator size, and basically pad the list out. So with 58, what would that be? That would be 64. Is that the closest? And that'll do it. So you could pad the overall length of the image paths list to be 64. Or we could use we could take a different approach, right, to performing this initial partitioning. So I think first, let's try just padding the length of our array, or of our list. So, you know, the way I would guess approach it, thinking on that now, is I would go, you know, get the number of paths. And divide that through by the size of my communicator. And I'll take the ceiling of that. I think that's seal. Ceiling. No, that is seal. Right. So I'll take the ceiling of that. And then just multiply that by my communicator size. So round up to the nearest number of elements, right? That can still contain my list, but be equally divided. And you know, hoping, right, that it's not too far off, we can just append to our image paths. Let's give this a more descriptive. Let's call it target endpoints. Descriptive name. So we can just append none. This array. And then in our loop down the bottom, we'll just go if path is not none, just to prevent an error. There we go. So that's one possible solution to our issue of having 58 images and that not being divisible by.
You'll need to import NumPy as well.
Yes, you'll need to import NumPy as well. Ethan? So import this NP. Okay. Give me a moment to think about that. Why is that? Let's think about this. So, where we are, just gonna take a sip of water. Getting the length of our paths, dividing that through by the size, which should give us some decimal number, taking the ceiling, and then multiplying that by the size. That should give us something that's divisible. And so, Jamie, how many processes is that? So that'd be 60, right? So that's the that should be perfectly fine, right? That's divisible by 4.
Yeah, running 4 processes.
Yeah.
and it's trying to split 60 up, but it's not doing it.
Mm-hmm. Okay. Is it because I have suggested that is it because we're scattering image paths and it's being sent to image paths? So local image paths, maybe. Let's give that a crack. Sorry. Image. Hmm. And does it execute fine with a single MPI process? So just setting n to 1. Okay. What could be occurring? Let's see. Okay. I think that come back to this particular error. So save a copy, and I'll show an alternative way to approach this problem that I'd personally find a little more straightforward. So using scatter, like we suggested, it's perfectly fine. However, we have a couple other alternatives. So I'm going to save this and make a copy. Which I'm now going to modify. So this sort of really, it all comes down to like, how important is it, right, that we're saving memory and that we're minimizing communication? All of this, like we have to consider that. And doing the scatter operation, one of the nice things about it, I guess, is that, you know, like we're performing that glob operation, so creating this potentially very long list of characters, and then we're scattering that. And that's going to, you know, save memory over, say, having a copy of that list at every single MPI process. But we would need to have a huge number of images before we start to run into any sort of memory issues when it comes to having multiple copies of our list. So like another approach to this exact same code doesn't really involve any MPI communication at all, because this is an embarrassingly parallel task. We'd still need to create our directory, you know, in the sort of rank 0 if statement to prevent that earlier error. But instead of the scatter, every one of our processes, MPI processes, can just glob all the image paths. And then we can just figure out a starting and an end index based on the rank of the MPI process and get it to operate over that particular slice. So a natural way to do that, sort of similar, right, to the padding approach we had before. So you need to count the number of images we want them to process from the number of paths. And here we're dividing it by the size of our communicator, doing the double slash. That'll round it down essentially to the closest integer. And because the ranks start at 0, we go, okay, so like the start index would be, and set that to the rank times the number of like images per rank. And the end index rank plus 1. Well, actually, we don't even need that. So just start index. Oh, no, sorry guys, I think it's clearer if we do this. We'll do end index. Okay. And you might then ask, okay, but we're going to run into the same problem. Like we're going to miss maybe some end portion of our list. Because here we're rounding down, right? So there's no risk in sort of the overshooting. Clamp it with a min. So I think I get the spirit there. Yeah, so it's sort of the way that I'd approach it is basically just set the end index equal to the length of the image paths if the rank is equal to 0, else we'll just leave it the same. And to account for the way that Python does its indexing, where it'll sort of go up to your highest index if you give it a range, or stop just before the highest index. Just adding a +1 there. So a parallelized code becomes path in image paths where we're just going to slice from our start index to our end index. Don't need to worry about checking whether or not it is none, it's not padding. And we've performed like very minimal alteration to our code. Ah, yes, thanks, Ethan. Yeah, hazards of coding life, right? So I don't want to perform that check at rank 0. I want to perform that check at the rank that is equal to the size -1, right? So the highest rank in my communicator. Yeah, how's that looking for everyone? Any questions about this? So like for me, this is a really great way to use MPI for time, so that you can identify that your task is embarrassingly parallel, so completely independent. Don't need to worry about communication. So, just loading the data, partition it up somehow like this, so just basing it off the rank, and then you're able to carry out the exact same process you had before. So you need to, as long as you've written your code to make use of Python, structures like for variable in list of variables, you barely need to modify your pre-existing code. And the really nice things about MPI for Python. So if you've managed to get that up and running on your machine, just please raise your hand in the Zoom. Great, good to see. You've had luck there, Jamie and Akbar. And Daniel. I mean, so Jamie, you asked earlier, like there aren't any errors, anywhere to check it's working. Like it's actually a good question. A few ways I'd go about this if you needed to have like a really wanted to check and be sure. Now I'd probably write this so it deleted, any existing files in my, resized images directory. Ideally, right? Because I'm changing the pipeline. I want to make sure that everything there is kind of new. And if I'm doing that, then I can form a glob at the end from a single process, and then check to see that it has the length that I'd expect. So it has actually processed all of those images. A step further would be maybe reopening all of the images and checking to see that they're all size 64. But in reality, you can get away, I think, with normally just checking to see that the same number of files are there, and that maybe one or two of those files has the expected file size. So they're the steps that I would take to check this if it was in a piece of mission critical software or data pipeline. So Brittany, your error, the size would come due to, sorry, I think my headset has disconnected. Can you all still hear me okay?
Yeah, I can hear you.
Great. Perils of Bluetooth. Right, so good question. So size, did you mean slice? That error is going to come about because this size variable hasn't been defined further up the program code.
Oh, I got a typo. That's why it didn't work.
Easy to do. Cool. Well, it's great to see a lot of you have managed to run that code. So yeah, this is a really common way to use MPI for Pi. Don't feel like you're not using a supercomputer to its full extent if you're not doing a bunch of scatter and gather operations. Like communicating over the interconnect is a necessary evil. It's not something we want to do. It just has to exist, right? To for us to be able to carry out a bunch of operations where we have data independency. But if everything could be embarrassingly parallel, then we'd be getting the most we possibly could out of all of our processors and GPUs. Cool. So with that, I'm going to proceed to the sort of final case study for this session.
Just a question before you proceed. So I've run it and I've got nothing returning. So does that mean that it's run successfully? It's just run the code without anything coming out?
Yeah, more than likely.
Okay, cool. Awesome.
If you look in resized images, you should see a collection of resized images. They'll be noticeably smaller.
Okay, great.
No worries. Thanks for asking. So I wanted to close off by looking at a slightly more complex, case where we would need to use a combination of point-to-point communication and also some collective communication. And that's for last case, which is a simulation of John Conway's Game of Life. Has anyone here encountered the Game of Life previously? So it's not actually a game. It's more so an early, to see you've come across it, Eric. It's a sort of mathematical game or toy that
John Conway invented some decades ago. And it's a really nice sort of example of basically chaos, right? Emerging, a very complex behavior emerging out of a simple set of rules. In the materials, I have an animation that show you how that kind of looks. Let's see. Oh yes, we can have a lunch break. Sorry, it is 12:54. Cool. Let's break for lunch, half an hour. So back here at 1:25, and we'll close off with a shorter discussion about the game of life. Thanks, Ethan. Didn't mean to go through lunch. Thanks for chiming in. Great. See you all back here soon. So for the last example, I want to look at something that's a little more involved, kind of show more of what you can do with MPI if you're have some sort of simulation-based or finite element analysis-based kind of project. You might not be writing this code yourself, but good to kind of see the sort of communication that's going on under the hood. We won't go through this one in detail, but we'll just kind of discuss the general approach and how it might be applied elsewhere. In particular, we're taking a look at a simulation of Conway's game of life, and it was invented by a mathematician, John Conway, in I think it was 1970. And it's the simulation of cellular automata. We start off with a grid and some random configuration of alive spaces on that grid. And depending on the number of neighbors, that cell either survives to the next step, dies at the next step, or it creates another alive cell, its neighbor. And just by picking these rules sort of carefully, and with even just a randomly generated initial configuration, we arrive at these very complex patterns and processes. So in fact, Conway's game of life is Turing complete. So you could actually implement Conway's game of life inside of the game of life. There's a Veritasium video where he uses that as an example, which I find quite amusing. And yeah, taking the website, right, you can see this animation, made a GIF kind of showing a simulation from an initial configuration. Hopefully it's playing down your end. And taking a look at the serial code, see it kind of consists of a couple elements. We have our game board, So that contains the alive, dead cells. So if it's either 1 if it's alive or 0 if it's dead. We have a loop for our simulation, so looping through all of the steps of our simulation. And to get the next state, we have this game step function that takes, so here U, that's the game board, so that's a NumPy 2-dimensional array. And this convolve operation that's doing is it's just essentially determining the number of elements that are alive with respect to each of the cells. And if there is exactly 1 neighbor that's alive, and previously, and if the current neighbors less than 2, it dies. If the neighbors would be greater than 3, it dies. Otherwise, we generate an alive cell. So that's the process we're carrying out for each of the cells. So each entry of our game board, which is stored as this NumPy array. So this is already a more complex kind of situation, right, than the other tasks. You can kind of see, right, the interdependency of each step is far greater, right? Every single cell depends on all of its neighbors for calculation of the next value. But we're still able to parallelize this. So even though all of the cells depend on their neighbors, we can take advantage of the fact that the relationship is only with respect to nearest neighbors. So a very natural way to approach this sort of a problem, so we consider we've got our game board. So a way we can approach this is to divide our game board into subarrays that are located on separate MPI ranks, MPI processes. So here we're seeing a case where we have 3 MPI processes. So this would be rank 0, rank 1, and rank 2. And for everything that is not at one of the boundaries, these red lines, the computation is parallel, right, with respect to it was independent with respect to our parallel partitioning. So for everything that's, 1 space in from this red line, we can compute our gain step as normal. Where we do require information is at the boundaries of our parallel partitions. And the way you can address that is we would have some sort of ancilla array. So we require 2 of them for our middle, and then just 1 for our top and bottom. And these can store information about the boundary cells, right, in their remote sort of process. So, these would be for receiving, and then you'd also have additional arrays for, well, you don't need the arrays for sending. So just to really emphasize that, I'm going to draw this orange, these orange rectangles. They're the cells that would have to send. So at the start of our parallelized game step, we'd begin by performing a sequence of send operations. So use red for the, I'll use another color for the sending. So let's say, sending to sending, yeah, purple. So right, we've got 0 would be sending to 1. And then, 1 sending to 2. And then we have the same communication pattern occurring in reverse. You can visualize this communication pattern as a line. So, we've got rank 0, rank 1, rank 2, and they're kind of connected to each other. They have a sort of a topology based on how they have to communicate. Now, the thing we need to watch out for, of course, in doing this is that we don't run into deadlocks. But if you're careful, right, about the order of the sends, it's not too difficult to kind of come up with a non-blocking sort of ring of send operations. For example, we can handle the sends at the top and the bottom independently, right? And then for everything else in between, in this case, just 1, could make sure that we are first, that for every one of the loops, what we first do is we check for, we first check for an incoming send from above. Then send to below. And that can be done inside of a Python loop. So the way I'd approach implementing this, it would be to first set up the communication pattern that I'm interested in. So basically create an arbitrary array, maybe, and distribute it. And that can be done simply by creating the subarray at each local rank. I would then populate it with the rank ID so I can see what is being sent where, and basically try to get that pattern up and running before I then introduce the simulation component. Because once I've established the communication pattern that I'm interested in, modification of that kind of game step function is relatively simple. All I need to account for are these additional sending and receiving ranks. So I need to either append them to my array or have something to kind of factor them in to the game step computations. And we'll just take a look at some MPI code that does just that. So here's a MPI parallel version of the, I'll need to share my screen. So here's a MPI parallelized sort of version of that simulation code. So the time step is still like, it's very much like the, in fact, identical to the game step function above. But all of the change sort of come in around how we are communicating between these subarrays. You can see that, we're starting off by generating our game state, so randomly populating the cells as either alive or dead. Then we use a scatter operation to distribute that evenly across all of our MPI processes. And then for every rank that is, that has a rank above or below, we're creating these row above and row below empty arrays to receive data. And then inside of our simulation loop, see first, okay, we're taking care of our top rank, so the boundary. So we know all we need to do there is send to the rank below. So we initiate that process. And for everything else in between, we first receive from the above rank, and then we send to the below rank. And because, right, the top rank doesn't need to send from above and it initiates, it starts off sending to the rank below. When rank 1 checks to see if there's an incoming signal, right, from or incoming data from above, it will receive it and then just proceed to that sending operation. So we've kind of set up that chain of events in a non-blocking way. And that carries on to our last boundary. So the one that doesn't have any rank below. And then we're using this as the sort of initiating step. So an initiating step to send the below arrays sort of up. So in this loop here, we're sending sort of cascading down. And then the sort of second half of our communication sort of cascade up. Now, once I've done that, I'm using this NumPy primitive to basically append the rows that I have received to my game board, and I can pass that to my game step function. Here it's NumPy time step, and compute the next time step of my simulation as normal. So considerably more code, but the underlying operations are the exact same as the the ones that we've looked at during this workshop. But together they're able to actually carry out something that's, it seems, I think, a lot more sophisticated. You may observe that in this example, I've used some of the non-blocking point-to-point communication. So that's the I receive and I send, so that capital I indicates non-blocking. You can also implement this with just the blocking point-to-point communication. Because this example is using the non-blocking point-to-point communication, however, I've included this MPI Commonwealth barrier command. So it's basically saying, hey, I want you all to stop at this point and ensure that all communication is complete before proceeding. And yeah, once the simulation is complete, I've gone through all of my game steps, or the population is, it's become 0. perform a final gather operation to gather my game board at the root process, and then I can save that state for later analysis or visualization. And yeah, really, that's I think where I'll leave it for today's workshop. Digging through this, it's not necessarily difficult, but it would take quite some time. But I just wanted to show you how a more sort of comprehensive use of MPI, how that kind of appears, and a use case of it. Maybe sort of trivial, simulating a scheme of life, but the same communication pattern could be used for solving a differential equation. Using like finite difference methods, or finite element analysis, where you're breaking your problem down into subdomains that depend on the values at the boundary of those domains. So it's broadly applicable, and there are other ways we can kind of partition our data. But for instance, we could not easily, but it's possible to implement, say, a 2D grid with columns and rows, our communication topology. So take a look at the chat. The MPI version requires you've made a results directory. The serial just runs as is. Thanks, Ethan. Yeah, that's something that I'll note to tweak. But you were able to run the code. By the sounds of it, that's great. Cool. So yeah, thanks for joining me. I hope you've picked up something that you might be able to use in your projects or a future project. Or at the very least, right? It's now on your radar. There's a lot of really great resources online for this. The MPI for Python documentation itself is pretty good. I'll share a link of some of the resources that I found useful when I post the recording for this session. And yeah, before we all head off, yeah, do we have any questions about the content covered in this workshop? Thanks, Daniel. Glad it was helpful. So Ethan asks if the MPI Game of Life version runs faster than the serial version. It does. Now, it'll depend a bit on the size of the simulation. So we need to make sure that there's enough work for each of the processes, the MPI processes, to do. So they spend more time computing than they spend sending. It may also be the case that on your laptop, you'd need sort of a problem of a size and sort of number of MPI processes, right, that sort of exceeds what you can sort of easily run, right, on a laptop with 4 cores. However, I know from experience, I'd expect you to see a speed up. If you set a large enough game board size, going from 1 to even just 2 MPI processes, there should be a noticeable speed up. Glad you ran the code as well, Brittany. yeah, I really like the. I'm a big fan of the game of life. I like all of the. I like the pretty patterns and the order coming out of the seeming order coming out of the randomness is very satisfying somehow. Great. Well, look, I'm going to end the recording. So goodbye to anyone who's watching this in the future. And I'll be around for a little in case anyone has anything else they'd like to ask about the workshop or internship.